This Late Night Linux Family podcast is made possible by our patrons. Go to latenightlinux.com/support for details of how you can join them. Support us on Patreon for access to ad-free episodes and early releases. That's latenightlinux.com/support. Hello and welcome to episode 137 of Linux Dev Time. I'm Joe.
I'm Amalith.
I'm Kevin.
And I'm Andy.
Good to talk to you all again. I'm led to believe that object-oriented programming was very popular once upon a time, and now that is not really the case. So I want to dig into why, but first of all, someone explain to me exactly what object-oriented programming actually is.
Okay, well, it depends who you ask sometimes. There's a lot of different definitions, but the basic idea is that you have your data and your code separated into different things that we call objects, and they talk to each other in relatively constrained ways. So you have, inside an object, you have the code can kind of do anything and manipulate the data in any way. And then between different objects, there's more separation. And often those objects map onto things in the real world, like a car or a road or something like that.
And some people will talk about it as kind of like a commingling of data and functionality, where you have data that you can operate on, but it's a distinct thing, for lack of a better term, an object. And you can perform operations on that data as part of that object. The reason it's nice, or why people have liked it, is because it maps very nicely to the way humans naturally think about things. We think in terms of things. The canonical example when you're learning about object-oriented programming is things like a car. And you can break a car, which is a distinct thing, into sub-components or sub-objects, like the engine and the wheels and the steering wheel and all kinds of things like that. And you can think about each of these components individually, which might have their own data and their own sets of operations, and that they all also work together in a larger object, i.e. the car itself, which might be part of a larger system and some other thing. So it maps really nicely to the way humans think about things.
And how we decompose problems into from something insurmountable to things we can actually reason about and comprehend. Trying to fit all of the workings of a car in your brain at once probably won't work very well, but maybe you can fit the workings of the engine in at a time.
In a way, it's just a way of arranging your code and your data that provides lines of separation between things. And also that means that when you're inside the lines, you don't have a line, right? You can mix things up quite a lot. If you're only working inside this one little object, then you're free to do everything so long as you don't step outside the lines. But when you step outside the lines, you've got to be more careful. You've got to have more kind of well-defined, clear ways of communicating with some outside object.
Right, this all sounds very logical to me and how I would approach development. So what's different now? What are you doing differently day to day that doesn't look like object-oriented programming?
Where this comes from a bit is that the cool languages like Go and Rust have declared themselves in some sense not object-oriented or less object-oriented than what used to be cool, like Java and C++. They are still a bit object-oriented, right? So some of this stuff hasn't gone away, but what has?
So one of the things that is good about object-oriented still, or rather one of the good things that existed, was that when you have objects, you can then start to separate some of the functionality from the data. So in other words, you can do things like instead of just a car, you could have a car and a truck, and you can talk about the things that both of those items might be able to do. So you might be able to say like something that can drive or is drivable. Maybe a motorcycle as well. All of those things can have like an interface of being drivable. And you can operate on each one of them without really knowing what the underlying kind is. Like you can, if the operation is just to drive somewhere, you don't really have to know whether or not it's a motorcycle or a car or a truck. So there are niceties, and other languages like Rust and others have kept some of those properties. Go is another one, but they do it in a different way. There are other things too that we can talk about with object-oriented programming, like better ways to do things nowadays. But like that is one of the things where like we've kept parts of it, but we do it in slightly different ways now.
Yeah, so I think it's time for us to get into some slightly more concrete examples. So anyone who's worked with a horrific enterprise Java code base will be familiar with what is generally referred to as like an unmanageably large and deep class hierarchy, right? So classes in Java are the way of describing objects. Critically, also the way of describing groups of objects like vehicle and stuff like that. So if you wanted to share some code between trucks and cars, something to do with the driving code or something like that, you might make this class called vehicle, and you might make another class called moving object or something. And then vehicles are an example of a moving object, and a car is an example of a vehicle, and maybe there's even more specific things, like a self-driving car is a type of car and so on. And you end up with these layers and layers and layers of stuff, and it can get incredibly confusing.
And in languages like Java, ultimately everything has to resolve back to like their top level class of like an object, like just the abstract idea of an object. And so you end up with all of these layers kind of arbitrarily deep and having to classify things in certain ways. And there's not really a good way to break out of that pattern. So some more modern languages, and probably also ways in like more modern Java as well, you can have some of those benefits of being able to share code between distinct things without this like crazy hierarchy of items all the way back to some root.
Yeah, so where it can get really tangled is if, like, I don't know, we carry on with the car analogy. Maybe you have like an indicator in a car which you press to signal that you're turning left or right. Maybe the code for that and the data for that, like, is my indicator currently indicating left, right? That's a bit of data. If you need to change the code around the indicators in this crazy hierarchy of classes and classes and classes, you don't know where the piece of data is that says, I'm signaling left at the moment. You don't know where the code that goes with it that lets you update that, and so on and so on. It could fit in quite a few of those different places, and it's easy to get lost. And even have multiple copies of that code that sometimes one of them applies and sometimes another one of them applies. And this is like an inheritance tree or a complex class hierarchy.
And further, one of the interesting things to me is you can even end up with like security issues because of this in some like lower level languages where you have greater access. So instead of the car analogy, if we thought of something like a cat and a dog, and both of those are animal types, and if you didn't really care what the underlying animal type was, you just like, give me an animal that has the ability to make a noise, right? A cat would go meow and a dog might bark. But in a lower level language, you might just have like a pointer to the underlying object, which you don't actually know what it is. You just know that it's an animal that can make some noise. The problem being, because if you have the ability to reach through that pointer and change the underlying type, you could have a cat that you make bark or a dog that you make meow, and other parts of the system that are relying on a cat to only be able to meow can break, and you can have security issues. So like there's all kinds of things that can pop up in these crazy contexts when you start trying to talk about things as an object.
I hope that gives some kind of flavor of why people got annoyed with object-oriented systems and decided that object orientation was bad. That there's this complexity about, does the data live in the more wide category or in the deeper category? And there can just be layers on layers and layers of stuff that's really hard to keep track of. And sometimes there's like policies in your company that mean you have to have a layer that signifies this thing and another layer that signifies this thing, and you end up with unnecessary layers and even more confusion. Maybe one of those layers is made out of XML, but let's not even go there. So there's a sort of a rebellion. And I first read about it when I was reading about Go and getting very excited about Go in the early times of me finding out about Go. And them just saying, we just don't need all of this. We need a place where we can put some data, and then we need to be able to say stuff about that place or that thing. So we need to have these things that we call interfaces, which describe what kind of shape the thing is, but don't hold on to any data. So like it can move, it's a vehicle and stuff like that. But if you actually want a real thing, then you're going to have to make an instance of a car or a truck and put your data in there. And it takes a lot of that complexity out by having just one concrete thing that can exist, but then lots of kind of views of it or categories that it fits into.
Another really interesting point that has come up a lot recently is something called data-driven development or data-oriented design, data-oriented programming. And in this model, you can actually have some data live out of band, which increases performance. So an example of this would be something like if you have, let's say you're building a game, and in this game you have a bunch of different types of monsters. And let's say you have monsters that can fly and monsters that are on the ground, can only walk or run. And in this type of a model, it might naturally be to have a piece of data included with the monster type that says like can fly, right? And it's a Boolean, true or false. So you could look at a particular monster, you'd read the field and say, can it fly? True or false, yes or no. However, it turns out with other models, you could just have, let's say, for example, you want to be able to go through all the flying monsters and do something like, I don't know, blast them out of the sky with some magical power. And to do that, you would have to go through all of the monsters, check this field, can fly, yes or no, and if yes, do something to it. If no, skip it. What you could do instead, though, is you could just have an array or list of all the flying monsters and a separate array or list of all the non-flying monsters. And here you've eliminated a particular field from your monster object or group, and instead kept that out of band. That has a bunch of different performance implications at the really lowest levels, but it can also mean that like the code is simpler to work through, and it doesn't rely on this like kind of big hierarchy of objects all the way up. You can start to organize the data in a way that is more conducive to the program and the language, rather than kind of how humans think about the problem.
And presumably that means that you could, for example, add another characteristic like can go invisible, say, and instead of having to then edit every single monster, you just create another list and put, say, half of the monsters on that list can go invisible.
Exactly.
Exactly. And so by giving yourself the flexibility of saying, I can describe things about this thing, but I'm not saying where the data goes, you get extra flexibility for that kind of thing. I'm just reflecting on it now and thinking that, like, if I think about Java in particular, which is like the language that really, really pushed object-oriented to the fore, I don't really think it was a mistake to like be good at object-oriented programming. I think the mistake was using object-oriented programming to solve every single problem that there is. Like in Java, there's no other way of doing anything. There's just this one hammer that you have to use to screw in all of your screws.
Yeah, and there are particular classes of problems that object-oriented programming is kind of nice for. Like it does solve a problem well. And in languages like Go or Rust, you'll often see people say like, hey, I have this problem and I want to map it in this way. How can I do that in this language that doesn't have this like really structured, enforced object orientation throughout the language? And the answer is kind of like, you don't. You have to think about the problem slightly differently, which ultimately, like in my opinion, comes to a better design for a lot of things. There are things that it does make a little bit more difficult to work around if you just happen to have one of those problems that maps really well to object orientation.
Yeah, so there's a great example with user interfaces. This is one that people always bring up. If you're building like a form with widgets and buttons and text boxes and stuff like that, then you quite often, when you're writing code to do with that user interface, you want to step through all of the things on the window and do something to them, like redraw them or something like that. And so being able to view these things as they're just all an example of a widget and they're different types of widget is just like very, very natural for how you might want to design that code. And if you take away some of the tools of deep class hierarchies from your language, it can be more awkward to solve some of the problems that come up in that situation.
Yeah, in those UI examples, a lot of times you'll have a function on the data called like render or draw. And everything, no matter what it is, will know how to kind of draw itself. And being able to like step through all of that and call the correct version of draw for all those things is very, very natural way to work in it. There's not really a good other way to do that without these kind of deep nested hierarchies of things on a page. And Rust in particular does struggle whenever there are deeply nested hierarchies or parent-child relationships that are difficult to describe in a way that is also easy for the borrow checker. So the borrow checker wants you to like be able to destroy something or own something, where in a parent-child relationship, there's not really an inherent, at least in a UI, there's not an inherent, this thing owns the other. They both kind of just point to each other. This is the parent, this is the child. And so in those things, there are languages that struggle with that. They don't have that like really deeply nested object orientation.
So Amalith, when you're writing Go, do you ever miss the stuff you can have in Java?
I don't think so. I would struggle to articulate the differences between Java and Go because I don't think any of my Java was so complex to have suffered from the deep nesting hierarchy issues.
Yeah, a lot of this is about culture. Like when I first encountered Android development, I thought it was really cool. It was all Java. I thought it was really cool because it was Java, but without a lot of the over-engineered complex stuff. Now, if you do Android development now, you'll be falling off your chair because Android development now is all about the over-engineered, complex architecture stuff. But at that time, it wasn't.
So what about in education then these days? Do people still get taught object-oriented programming?
In university, all of our courses were around object-oriented Java, but after I graduated, they've since switched to teaching Python, but I don't remember whether that's object-oriented Python or normal Python. I don't know how to refer to the not object-oriented Python.
Yeah, my kids at school learn Python without really mentioning classes and stuff like that at all, or if they did mention it, only right at the very end.
I've seen fewer classes nowadays that jump off with object-oriented programming. Back in the day, it seemed like everybody was teaching object-oriented programming because it was like conceptually very simple. You'd be like, hey, here's a cat and here's a dog and they can both speak. But nowadays, people seem to focus less on the classes and objects and more on doing a particular thing, which I both agree with and disagree with in some contexts. I still think you end up having data that you have to encapsulate in some way. But I like the fact that there's less focus on trying to fit everything into an object and that object into a bigger object and that object into a bigger one. I like that they are, I think, guiding people towards a more modern approach.
I'd like to make an analogy here, though. Well, I was talking to my son the other day about Freud, and he was saying about how everything Freud said was completely wrong and weird. And I was making the point that the stuff that Freud said that is not weird is now completely accepted, right? So the idea that you can have therapy and talking about things can help you feel better. But then some of the other stuff, yeah, we might want to throw out or question or reinterpret. And similarly, I feel like object-oriented programming is like completely embedded in the way we think about lots of programs, including, say, even in functional programming, we still kind of capture data into a place and then have code that operates on that data. So in some sense, object-oriented programming is like completely embedded and we just all do it. But then we're throwing away some of the bits that maybe we're going a bit far or weren't quite the right direction.
It's funny hearing you talk about Rust and some of the limitations of it, I suppose, makes me think that diversity is good. Shocker. Like when it comes to languages, like you can't just do everything in one language, in one style. You need to have more flexibility.
Yeah, that's one of the things that I like to tell a lot of the more junior engineers that I work with is try out different languages. Try new paradigms of languages that you've never even tried before, because learning how to think about a problem in a different context entirely is very liberating and eye-opening. And being like almost dogmatic on a singular language or paradigm can be limiting in the greater scheme.
And also, just some things are just better for some tasks. Like one easy example is if everyone learned programming by learning Rust, then like no one would learn programming because it's too hard.
And even like a lot of the modern languages now, or like more modern languages that are coming out, like they're always trying to take good ideas from across the programming language theory, like all of the various languages. They're trying to pull out good parts of all of it. So knowing a bunch of different things and how things work and how they don't and which paradigms work well in what spots, like that's very critical to future development careers.
Yeah, learn all the languages, partly because it makes you think better, like you bend your brain to think in a different way, but also you could just find yourself in a context where deployment is way easier if you know PHP or whatever. Like just learn all the languages. It's fun. But anyway, back to object-oriented. What do we really think has actually changed between the way code worked before and how it's working these days?
Well, one of the big ways would be how we shared functionality between various pieces of code. So in the object-oriented way, we would share it by inheritance or the like sort of parent-child relationship or those big class hierarchies. So you would have like the top level object would have the most generic functionality. The objects below it, like its children, would specialize and they would say like, yeah, we do that thing, but we do it in this particular way. And the objects below that would say, yeah, we do that thing too, but we do it in this other special way. And you do that via these inheritance hierarchies. Nowadays, we do this, or at least in other languages, we do this more from a composability method where we can share functionality via interfaces. And there is a way to think about this versus people will say a has a relationship versus an is a relationship. And whether or not you have objects you can operate on or different interfaces, or whether you are an interface and you are a thing. The is-a is more of like a hierarchy, those class object-oriented version. And then you have the has-a where you like have lists of things that you can operate on or operate through. And you have a bunch of different objects that you can operate on, but you are not itself an object.
So that made me think of like some of the most concrete ways of explaining the problems that you can get into is if you have one of your more high level general classes defining a piece of functionality. I'm desperately trying to think of an example. Let's say, we're back to a game where, the monsters can shoot things, right? So there might be a method on a monster called shoot, right? Which is actually implemented at a very high level. Like all monsters know how to shoot and they all shoot these normal bullets. And then there's a particular type of monster that has like a flamethrower or something like that, right? So that monster has its own version of the shoot method. And so now there's code in the monster class that tells you how to shoot, and there's code in the flamethrower monster class. And as a poor programmer trying to debug this later, you end up spending like half your day reading the code for monsters before you realize you're actually dealing with a flamethrower monster and you were reading the wrong code. It's really hard to figure out where it all lives. And if you contrast that with the kind of has-a style, you would have a monster that inside it has a like flamethrower gun or something. I'm sorry for the like shooty guns analogy. Then it would be very clear, like that type of monster has that particular type of gun and there's no ambiguity about which code's going to run when you use it.
And why this can also be somewhat unintuitive to the way that we think about problems as humans, which I keep going back to, is in the analogy of cats and dogs, it is more natural to think of like an animal, and an animal can make a noise, and both a cat and a dog are an animal, right? They both have the like make a noise function. So that's a very natural way for humans to think. It's kind of inverted if you have a dog object and a cat object. Both of them have a like speaker module or something along those lines, where they have a thing that implements an interface versus they are a thing that implements an interface. But it turns out that composability is more powerful in many ways or in many programs. And that's why we've kind of moved to that, even though it was slightly more unintuitive to the human brain.
Yeah, I think that's a really important point, actually. Like, it is slightly less intuitive, but it turns out it works a lot better in practice.
Right, well, we'd better get out of here then. We'll be back in a couple of weeks, but until then, I've been Joe.
I've been Amalith.
I've been Kevin.
And I've been Andy.
See you later.